So now I can form the mean. Once I know what these probabilities are, I just average the mu's over iota, form mu bar t. And now the decision maker. The decision maker is using data. The decision maker doesn't know iota. So here we're back to this notion of reducing compound lotteries. We want to go back to what the information structure that's relevant for the decision maker, and that's just the histories of x's. So there's a different evolution equation that captures, that's represented in terms of the history of things which the econometrician here actually observes, the x's. And that's dxt is equal to mu bar dt. Mu bar doesn't depend on iota here, it's been averaged out. Sigma of xt. And now the way this works is this new Brownian motion here, w bar t. Okay, you'll have to trust me on that. But the interesting part of dw bar of t is it's the original one, plus it's got this other piece here. Mu, it's got this forecast error or prediction error. Mu xt iota minus its conditional mean dt, sigma of x inverse. So really what you've done here is the following, and this is what is either intriguing or peculiar about this continuous time limit, is sigma's the same even though I've reduced information. I've reduced compound lotteries here. So yes, I've changed this I had to change this object, but the amount of risk locally that shows up is going to be quantitatively the same because this has the same covariance structure as before. It's the same sigma that shows up here. So taking this continuous time limit, locally, the amount of risk remains the same. So this, I'm asking you to trust me that it's the case. It's roughly kind of a corollary of this type of observation here. This has some rather spectacular consequences. One observation is, why not be Bayesian? Well, if I'm going to take a Bayesian approach, I'm going to say I'm going to do this reduction of compound lotteries. Locally, this decision maker is facing the same quantity of risk as he was before. Once we solve the Bayesian decision problem. And so what that means is if I do things like local risk-return trade-offs from finance, they're going to be the same, even though I've reduced information here. So under this limit, things like risk-return trade-offs are invariant. So yes, the Bayesian approach, the straight Bayesian approach here basically leaves in place the risk-return trade-offs, invariant to whether we observe iota or not. So estimation error is just not consequential there as a consequence of this, which is truly bizarre, right? I mean, it seems like there's a econometrician struggling to estimate iota, but its consequences are so subtle locally that it leaves in place the original risk-return trade-offs. What risks get traded, of course, matters here, because you can't trade these guys. These guys aren't observable anymore. You have to trade the risk, these type of risk, but they remain the same. So a learning story, it turns out, doesn't alter. A Bayesian learning story doesn't alter risk-return trade-offs, which is and so the type of stories that we want stories that under which estimation really has much more potent consequences. Okay, so we're going to have to. Okay, so that's the first observation. Does this seem like nuts? It's kind of wild, isn't it? We've reduced information, and it's not the same risk-return trade-off. So one argument you can make is, so why do this continuous time limit, given it gives this silly result? Okay, but we're going to use it instead as saying, well, it's going to motivate us to look for other avenues to get big impacts on things. Yes?
So if you did this in discrete time,
yeah,
you would get an impact, right?
You would get an impact that would become vanishingly small as you shrunk the tau over here.
Right.
Right. It's going to get smaller and smaller as tau gets small. Right. So one of the criticisms about this so-called smooth ambiguity story just has to do with the fact that once you make this observation, anything you do about simple risk aversion over here doesn't have much consequence. So it's pretty much.
Sorry, can I?
Yeah. Ask away, please.
Yeah. So
me
you're
too.
averaging over the models using the steer, right?
Right.
So why are you doing that again? You're just-
That's what a Bayesian tells me to do, right? I go read Savage, that's what he tells me to do.
And you're going.
So we're gonna do something. I mean, we're gonna now push away from this, but this is a standard decision theory approach. Here, there's it says reduce. It says take your original information specification with the iotas there, but you don't know the iota, so you estimate it. You estimate it using likelihood methods, and then produce a new evolution equation for the data for the x's here, based on past data. That's what this is. You know, suppose you go to your regression class, okay? And so you write down this regression model, but you don't know the regression coefficient beta. A decision maker is not going to care. The decision maker uses that model only to tell him how to get the evolution of the future data given the past data. And so it's going to replace some type of estimate for beta or kind of do some type of Bayesian calculation, just as a way to get something that's operational. What's my best forecast of the future given current and past data? And that's just what this step is. So this is.
Could you go back to just the original, just the original?
One earlier slide?
No, all the way back, right there. Yeah. Yeah. So you made a decision to make mu depend on iota, but not sigma.
Right. So that's an I mean, okay. So as I say, one reason for that is if the sigma, it turns out if it's very smooth over time, you can figure it out exactly. The other one is, although there's recent work which I'm not going to get into here, recent work in probability theory that kind of generalizes this model and makes the sigma estimation interesting. We're not going to go there today. So there are ways to change this environment to get interesting challenges for estimating this piece. So we're going to focus on this one. Okay.